Okay, in this short video I want to try and explain how ordination procedures can allow us to extract and visualize the important patterns in complicated sets of data. And I'm going to use the set we're looking at here. Again, as is often the case, this is invented data because then I can set it up to show exactly what I want to illustrate. So here we've got a set of 12 samples, 3 replicates at each of 4 sites where we're looking at the ground. And I have counted the worms in the soil and the number of snails. And these, given the counts there, 66 and 86, these must be fairly large plots. I've also recorded 3 environmental variables: the amount of light, the soil moisture content, and the percentage cover of grass. So I've selected the whole set there and do the usual copy, Control C, over to PAST, edit labels on, and paste that in and turn the labels off. Now the first thing I want to do is make it easier to look at the results by going to Edit, Numbers to Color Symbols. And so I've used the site numbers here to label and color the rows. And remember, as always in this kind of data, the columns are the variables and the rows are the samples. And some of the columns may be indicator variables telling us which site or which replica we're working with. Now, it's traditional to have the environmental variables first, so that's easy to manage in PAST just by dragging. But I want to start by looking at the worms and snails. Now, as there's only 2 species here, it's actually easy to visualize these results just with a scatter plot. So over to Plot and down to XY graph, and then let me fiddle with a little bit. Point symbols, thick lines, larger symbols, not that large. And let me make the whole graph easier to see by making it a bit bigger. Okay, so now you can see a scatter plot where I've got numbers of snails against numbers of worms, and you can see that there is a fairly good relationship, so that a plot that has few worms tends to have few snails, and the other way around. And there's also some separation among the sites. So the 3 red dots are all up here, and they tend to have high numbers of worms and snails, and in contrast the green dots are down here at the other end. They tend to have less or lower than average numbers of snails and worms. Now, one thing we can note if we look here, most of the variation here is along this linear axis here. And if we go side to side this way, there's not much variation at all. So we could actually summarize this information by focusing on the main axis of variation. So let's have a look at doing that. So I'm going to work with the same data, but I'm going to go multivariate. Normally for biological data, counts of species or measures of species abundance, we do non-metric MDS. But to start with, I'm going to do principal coordinates. And principal coordinates is like principal components, but it allows us to select the similarity measure that we wish to use. Principal components, which we'll come back to in a little while when I look at the environmental data, principal components implicitly uses Euclidean distance. So here we go. And principal coordinates here in past defaults to Euclidean, but I can switch to Bray-Curtis. And note, down here we've got 2 columns. Don't worry about the eigenvalue, worry about the percent. The percent axis there tells us how much of the variation in the data is captured by that particular axis. So you can see nearly 91% by axis 1 and another 3% by axis 2. But axis 1 by itself extracts most of the variation. And if I go back here to my scatter plot, that's because a lot of the variation is along this linear axis here. So let's have a look at what the scatter plot looks like. And again, I will tidy up this graph to make it a little easier and resize it. Now, what's happening here? If we look, most of the variation here is going across this way, and some of the variation is going up this way. Now, note first of all the axis scaling down the bottom. It goes from minus 0.25 to positive 0.15. The side axis, the y-axis, is working with much smaller numbers, minus 0.03 to 0.02. So the y-axis variation is something like 1/10, 1/15 of the x-axis, and that goes back to the 90% of the variation that is captured by axis 1 or coordinate 1 and the 3% that's captured by coordinate 2. Now I can put row labels on here, and if we look here, what have we got? Up here on the right hand side, 3 red dots. So the 3 samples from the red side, which had the higher abundances of both species, are over here on the right, and the 3 green dots are over here on the left, and those were the sites which had lower abundances of the 2 species. Now, because we have only 2 species, the graph we're looking at here for the principal coordinates analysis is not really telling us anything different from the graph here, which is a linear scatter plot. All it's done is coordinate axis 1 is going this way, and coordinate axis 2 is going this way, and the graph is, or the principal coordinates analysis, is really just rotating this graph so that this linear increasing axis here just goes straight across the page. If we look at the order of the dots, green, blue, black, green, green, blue, black, green. Now, the beauty or the usefulness of ordinations, whatever technique we're using, starts to come in when we've got more than more than 2 variables. So if I get out of this, now let's go back here and look at the environmental variables. We've got 3 environmental variables here. Now, I actually haven't tried to do a 3D plot, so I'm not going to try and quickly do one without testing to see if it works. We could do combinations of scatter plots to look at what's going on here. So I can go, for instance, light and moisture, and this time I won't bother fiddling with the graph to make it prettier, but I will make it larger so you can see it more clearly. I need to make the symbols bigger, so I may as well. Okay, and we can see a similar sort of pattern here when we're looking at the relationship between moisture and light. For instance, green, blue, black, green, green, and the three reds are up the other side. But to look at these relationships, I have to either do a 3D plot or do 3 scatter plots. And once we get past 3 variables, it starts to get more complicated. So what we want to do now is, can we use an ordination to simplify these patterns to extract the major part of the variation and allow us to look at that? Well, for environmental variables, as I talk about in other videos, we will traditionally look at principal components analysis. So here, principal components. This is going to use Euclidean distance. Now, whenever we start to use a distance measure like Euclidean distance, and whenever we're working with environmental variables, we have to think about the scale. So over here we've got light. I can't honestly remember what units light is measured in, but it's some measure of energy arriving per second per unit area. Moisture is a percentage, and it could go over 100%, because if the soil was super saturated, there could be more than 100% moisture in there. Grass is a percent, but it can't be more than 100%. When the plot is completely covered by grass, we've got 100%, and it can't go less than 0. So we've got 2 things which are percentages and 1 which is something else. These are measured in very different scales. And if I change the measurement of light by rescaling it or using a different unit, I'll have different numbers and we'll get different results. And that doesn't make sense. So what we can eventually do here is transform these results. We normalize the variables. Now in PCA, in past, there's a quick way to do that, or a quick way to get the same result. Instead of looking at the variance-covariance matrix, which focuses on the actual measurements themselves, we can use the correlation matrix, and you'll see the numbers change slightly. And the results we get here are similar to what we had for the principal coordinates on the animals. A large amount of the variance, 95%, is associated with axis 1, another 5%, or a little bit less than 5%, with axis 2, and the last part with axis 3. So let's have a look at the scatter. And again, we'll add a bit of fiddling here. So when we looked at the scatter plot for 2 of those variables, again there was a Again there was a relationship going up. So there was a linear relationship going up, and that variation, that information, has been extracted by the PCA and is now principal component 1 going left to right, or the x-axis if you want to think of it that way. And that captures, as we just saw, 95% of the variation in the data. The axis 2 here captures the remaining, or most of the remaining, 5% of variation. So most of the information about the relationship of these samples is in this first axis across. And what do we see? Green, blue, black, green, green, and the 3 red are up on this side again. That's not particularly surprising. We might expect the biota, the animals there, to be displaying patterns that are similar to the underlying environmental variables. Now, with the PCA, I can put on the biplot. Can't really do that with the principal components ordination yet. It's not implemented. So variation up is moisture in the opposite direction to light and grass going down. And here it might be useful to also look at the loadings. So let's just make this one bigger. So axis 1 is measuring light, moisture and grass, and all of those three things contribute more or less equally to going from the left side of axis 1 across to the right side. So if I bring this back up here, down here we've got low levels of moisture, light and grass, and up here we've got higher levels. Why don't these lines go straight across? Because they're also capturing the effects of axis 2, even though that is a very small percentage of variation. So if we switch over here, we'll see that axis 2 is really a contrast between light and grass and moisture. So back to the PCA, these samples down here will have higher levels of light and grass, and these samples up here will have higher levels of moisture and lower levels of light and grass. It's important to remember back from the original results that 95% of the variation is across this way, so that's the important difference among these samples. It's lower light, moisture, grass over here, and higher of those three environmental variables over here. Okay. Now, so what the ordination allows us to do is to look at the samples and find out what things, or what combination of things, are most important in terms of separating those samples. What's the important variation? Now, I said earlier normally we would do MDS for the biota, so that's what I'm going to do now. It's the last thing in this video. Multivar down to non-metric MDS, and number of environmental variables 3. Now, if I don't select the environmental variables, I can just do the biota on its own. Preliminary measure, so we will use Bray-Curtis, which is usual, and tidy up the graph as usual. And lastly, resize. And let's have some labels. Now, important thing to remember is that the MDS is putting the points onto the plot in terms of just the abundances of the taxa. It's not paying any attention to the environmental variables when it is positioning these samples. Second thing to remember, unlike PCA and PCO, we cannot with the MDS get any idea of how much variation is being extracted. That information is not available to us due to the way in which MDS works. MDS works by looking at the ranks of the I was going to say symbols, but the ranks of the samples. So there's two samples that are closest together in terms of their distance will be put closest together on here. But it's not looking at the actual distance, but the ranked distance. So these two samples, the distance here between these two would be given rank 1 because it's the smallest, and so on. So the plot we're getting here, and I'm going to come back to the vectors in a moment, the plot we're getting here is rather different from the plot we got from the principal coordinates. Or is it? Let's have a look here. I'm going to start at this end. Over here, green, blue, black, green, green. And up the other side, red, red, red. The only thing that's really different is that this graph is flipped around. Now, the orientation of ordinations doesn't really matter. So if I were able to flip this, other programs just allow me to tick a box and flip the graph left to right and up and down, but I can't do it here. But if I was able to, I would end up with a pattern that looked fairly similar to what we saw from the principal coordinates. Principal coordinates, I keep getting confused. It won't be exactly the same because these two methods, principal coordinates and NMDS, are looking at somewhat different sets of data. One is looking at ranks, one is looking at the actual distances. Now let's go back and have a look here at the vectors. You'll see they're pointing in the same general directions as from the PCA, but switched around left to right, and that's another clue that this graph is flipped compared to the PCO and the PCA. But we've still got moisture going off one way and light and grass going off virtually identical in the other way. So down here, low moisture, light and grass. Up here, higher moisture, light and grass. Up towards the top of the graph, higher moisture, lower light and grass. Down to the bottom, lower moisture, higher light and grass. Now, I said the NMDS did not take into account the environmental variables when plotting on the points. So where do these come from? What it's looking at is the correlation between the environmental variables and the axes of the graph. And that's how it works out how to put these lines on. But the information is basically the same as we're seeing from the PCA. Okay, out of here. So to sum up, if we've got just two variables, we can look at the patterns and see all of the information just by looking at an XY scatter plot. But if we've got three variables, it starts to get more complicated because we need to either look at a 3D plot or look at sets of 2D plots. Once we've gone beyond three variables, it is very tricky to do. But using ordination techniques, we can extract the most important information, or we can extract the variation that is associated with changes or differences among the samples and display that in a simpler space, a two-dimensional space, or occasionally a three-dimensional space.